Up to this point, we have been discussing situations where uh, objects were in thermal equilibrium, and so we would look for a situation where the temperatures at the end of the process were all the same. But what if you have a situation where you've got two objects that are not in thermal equilibrium? How does how the question arises of how fast the energy passes from one object to another. And when considering that, there's also the question of how that energy is transmitted. There are two main descriptions of energy transfer that we're going to be talking about. We're going to have mathematical models for um, in this chapter. Conduction is where two objects are basically touching. Radiation is where energy passes between them by light. And when I say light, this includes light that is visible, but it also includes light that you can't see, infrared and ultraviolet light. There's also the mention of convection, which doesn't really have so much of a mathematical model. You could develop mathematical models for wind and currents, and there's also just carrying a hot object from one spot to another, which would be a form of convection. I'm also going to say that conduction, there are two sides of the same coin. Conduction and insulation are essentially uh, connected in a way, because when you have a conducting material, or when you have heat conduction, you might also put a material between things that is called an insulation. And basically, conduction is something that is a good heat conductor is something that is a bad insulator, and vice versa. Conduction and insulation aren't really associated with any named uh, equations. Radiation, on the other hand, is associated with a named equation called Stefan's law, and it is also associated with a quantity called the emissivity. And they don't really explain the emissivity in this text very clearly. I have kind of my own ideas on it. But essentially, it comes down to this. If E is equal to 0, it's transparent and dark. It doesn't give off any light, doesn't absorb any light, doesn't give off any light. E equals 1 is associated with a full spectrum light. It absorbs all the light that comes in and gives off a full spectrum light that looks like white. And if 0 is less than E is less than 1, you'll have some colors that are enhanced and you won't have the full spectrum, but it ends up looking kind of like a colored light. Now I'm going to show you a couple of graphs that are associated with the full spectrum white light. That is, and it's called a Planck spectrum. It's not, we, and what happens is that there is a some light, there's like a whole bunch of different light frequencies coming out of a star. And depending on the temperature of the star, you get different levels of light from each frequency. Some of these frequencies are going to be in the infrared spectrum, and some of them are going to be in the ultraviolet spectrum. And you can see this is called Planck's law, and here's a graph of basically it's a histogram of the wavelength versus the power, uh, kilowatts per steradian per meter squared per nanometer squared. Anyway, the power at each wavelength. And in a 3000 Kelvin star, that is it's kind of a cold star. You have a lot of infrared light and just a little bit of visible light and just a tiny bit of ultraviolet light over here at the edge. These stars are often called red dwarfs because there's more light given off in the red spectrum than there is in the blue spectrum, and the star actually appears red in our telescopes. Meanwhile, at a 4,000 Kelvin uh, surface temperature, you get um, the a little bit more yellow light and a little bit more ultraviolet light. With a 5,000 Kelvin surface temperature star, this is pretty much centered on the visible spectrum, so that would end up being close to a white colored star. There are even hotter stars that end up looking blue because they end up with the higher area being over here and less red, and those are gigantic stars generally. But all of these are examples where the emissivity of the object is 1. It's a full spectrum light. On the other hand, LED lights or light emitting diodes, they're carefully designed so that they only transmit light in certain frequencies, and they're generally designed so that they only create light in the visible spectrum, and any light that they produce in the ultraviolet or the infrared is wasted energy because a person can't see those colors, and but ideally they're going to have a value of E that is as close as they can get it to 0, and still produce a light that produces a full spectrum between 400 and 700 nanometers, which is what light humans can see, and as little light as possible in the other colors. Now that's great for humans, but where we see this rich tapestry of green, yellows, and reds, your poor dog only sees this bland yellowish color. And apparently where we see the color purple, the dog sees colors of blue. So our eyes are not really designed to tell us whether something is a true full spectrum of light or if it is some kind of colored light, because we can't distinguish between a true full spectrum of light and something that just has a little bit of red and a little bit of green and a little bit of blue in just the correct values. Basically, we have tiny little cells in the back of our eyes that can detect blue light, green light, and red light, and the different frequencies of light um, hit our those what are they called, cones, in different proportions, which gives us the experience of seeing these colors. So without further ado, let me give you the radiation equation, which is Stefan's law, and the insulation and conduction uh, formulas, which don't actually have a name. I'm going to start by giving you the radiation law, which is called Stefan's law. It kind of comes up a little later in the chapter, but it goes power equals sigma A E T to the fourth. And so sigma is the constant. It is 5.67 times 10 to the negative eighth. And that's kind of fun to say because it's 5, 6, 7, 8. See, isn't that cute? But that's in watts, which is the unit of power, per meters squared, which is the unit of area, and Kelvin to the fourth, which is the unit of temperature to the fourth power. So sigma is just this constant, and it's called Stefan's constant, or yeah, I think it's sometimes people call it the Stefan-Boltzmann's constant, but we'll just call it Stefan's constant. Oh, no, actually it is Stefan-Boltzmann's constant in our book. Okay, so anyway, Boltzmann's constant, K sub B, was equal to R over N sub A. So don't confuse Boltzmann's constant with Stefan-Boltzmann's constant. Okay, then E is just how much, what portion of the full spectrum of light you have. So 0 is less than E is less than 1. It's some number based on whether you have a radiating body or not. If it's fully radiating, it's 1. If it's not radiating at all, it's 0. And then A is just the area. It's just the surface area that is letting out this light. And T is the temperature in Kelvin. And so one area where I've seen this applied is considering the temperature of the sun. The surface temperature of the sun is, I think, usually regarded to be somewhere around 6,000 Kelvin. So you take 6,000 to the 4th power, which is just an ungodly huge number. And then you multiply it by the area, the surface area of the sun, which is 4 times pi times its radius squared. You assume that it is radiating in full spectrum, so E is 1, and then you multiply that by this 5.67 times 10 to the negative 8th watts per meter squared per Kelvin to the 4th, and that gives you the power of the sun. And the power output of the sun and tells you how many joules per second is being released from that gigantic furnace. It comes out to be 3.8 times 10 to the 26th watts. I like to convert it to 10 to the 24th and refer to it as a yotta watt, just for fun, because I think 380 yotta watts is a lot of watts. Things get a little bit confusing though, I think, with equation 11.11, because equation 11.11 sort of puts the radiating body in basically in contact with another body. So we've got the area here, we've got a temperature here of the radiating body and the temperature here of the body that is radiating back. So we have a net power coming in of sigma coming from, let's see, if the power is going that way, I think, yeah, then the power is equal to sigma A E t to the 4th minus t sub naught to the 4th. So that is a description of how much power is going from this region to this region to this region. However, we've already got an equation for objects that are in that kind of contact. Equations 11.8 and 11.9 basically do the same thing, except instead of having them just connected that way and transferring temperature through radiation, we're going to put that same area, but we're going to make it a little bit of a thickness to it. And when we add a little bit of thickness, and maybe we've got more than one substance, so we'll have a layer of this in a thickness and a layer of that in a thickness, and then maybe another layer of something else with a thickness to it. And then that sum of layers with their thickness is what is this sum of layers and thickness that's on the bottom. And you'll notice that for these, instead of that t to the 4th minus t to the 4th, there's no 4th power in these. It's just a linear operation for the conduction. Okay, basically, Boltzmann's law is the first equation here. P equals sigma E A t to the 4th minus t sub naught to the 4th. And the insulation and conduction law comes out to this, which I will describe in the next video, where we have a linear t minus t sub naught. And I haven't quite worked out any resolution between the two, since this one involves a difference in temperature to the fourth power, and this one involves only a temperature difference in the temperature to the first power. But under different situations, it should probably be clear in our text which one of these we should use. I was trying to get them to resolve to the same thing using a little bit of calculus here. I think the derivative of t to the fourth is 4t to the third. So I wanted to see if I could make this with a kind of pull out that dt and see if I could find where that was equal. But I got a little ways, but I wasn't really finished with that project. Anyway, you can ignore that and just note that these two things, these two equations will be applied in different circumstances. They aren't exactly compatible, but it will be pretty obvious under which circumstance and which of those two equations you should use.